Hello, replay attendees. Glad to see you today. As you probably can say by my accent, I'm not from Bellevue. I'm from Belarus, which is a quite different place. But the reason today is because 5 years ago, a single tweet actually changed the whole direction of the way how I think and how I perceive the software implementations and the software architecture. And today I'd like to tell you the story from this tweet to the moment once we start implementing AI workflows in our applications, in applications for our customers. So my name is Anton. I'm the CTO of company Spiral Scout. We provide software development for our customers around the globe for around 15 years. By a person who is maintaining the team and tasked to make sure that we do a good job, as a tech leader, I have to always make sure that the job and the task, the tools we use is always optimal, and we don't spend additional time on doing the typical bootstrap code or anything that, well, we don't want to do. As a passionate coder, I love to mitigate that by actually creating my own tools. And for the span of my career, I created a number of open source instruments, well, and closed source instruments, everything from frameworks to ORMs to database layers, template and agents in DSL, and etc. But as time been passing and our client pool been growing and the complexity been growing with it, we soon realized that even we have our own toolkit and the team which knows that to use it, and back in the day it was mostly PHP, we have been lacking one of the very large abstractions which have been seemingly hard to get. And this abstraction, as you guys know today by this presentation and this conference, is workflow engine. So what the first logical solution that every engineer will do if he cannot get the instrument he wants in his stack? Well, let's build it itself. Very smart idea. So we started doing the research and started to look in the ways how we can start implementing the workflow engine in our products. We used to work with Amazon SWF, and it looked like a very nice solution for many things, but it still was quite proprietary and hard to use in ecosystems like open source or outside of Amazon. At this moment, once I had my first prototypes, we soon realized that amount of edge cases that we uncover by running this engine just grow exponentially. Every day and every moment, we've seen more and more problems arise from the things we expect just to work. That's the moment where I decided to come back and try to do additional research and see maybe there's a new tools in the market, maybe there's a new solutions or some better patterns. Around the time, I found a similarly well-experienced guy on Twitter who was talking all about workflows and durable executions, the patterns that they can implement, and applications that can run for the span of days and months, and etc. So I thought myself, okay, he has his solution, I have my own stack. Why not try to talk to him and see if we can collaborate to bring it in? So I wrote a Twitter message. And so to my surprise, this person said, yeah, let's talk. So 5 years ago, by conversation with Maxim Fateev, it kicked off the quite long collaboration in which we created the Temporal PHP SDK, and we began to use and adopt Temporal for our own products and for the products of our customers. So at this moment, everything looks very nice and cozy. We have our own stack, we have powerful workflow engine. What else can you dream about? What else do you want? And that's about the moment where GPT-3 dropped on the market. Once you see this model and once you realize what state-of-the-art LLM can do, they can interpret your user requests, they can make haikus, making jokes, or help you to process any information, it becomes very obvious that there is an immense potential how we can use these solutions to build something more complex. Yet, we've seen that while implementing this solution and building our first pipelines, summarizing tweets, making the pull request reviews, and etc., we've still been seeing this pattern over and over that even if you have this powerful technology powered by state-of-the-art models built by very powerful companies in the world, the actual process of implementation is not that different from 20 years ago. You still go through the planning phase, design phase, implementation, and iteration. So we kind of seen a situation where we have these keys from Lamborghini, but we use it just to drive to Costco. Why we still have these powerful models that we cannot actually use to enhance our main work? These days, we have copilots and we have many other tools, but we decided to actually come back to the drawing board and challenge ourselves to a bit different question. Can we create the software that can not only be programmed ahead of the time by engineers, but the software that can actually program itself and expand its own functionality as it goes, with collaboration with user, and why not, maybe by itself, just trying to see how it can be optimized. By this moment, we clearly know that this is going to be a very challenging task. It's going to be a very complex architecture, which is going to be spanning for many domains and many parts of the system that has to be collaborating seamlessly. Well, only if you have some nice engine that will help us to cope with this complexity. With this engine is obviously Temporal, since I'm speaking here today. So let's try to dive and see what we can do in terms of LLM payloads and LLM workloads within your Temporal application. So the first what we have to do to talk about that is to properly define the boundaries, how we actually define the LLM calls within our workflows. And surprisingly, in terms of the actual workload implementation and in terms of the actual workload data flow, the LLM can be defined quite easily. It's a black box, and many engineers actually define them as a black box as well. It's very powerful and magical abstraction. You put some data in, you get some data out. Sometimes this data is good, sometimes this data is just garbage. Well, that's something we have to live with. But at the same time, as you guys know when you use LLMs, while this solution has been extremely powerful and extremely versatile, at the same time it's quite unreliable. You will be seeing everything from failures on API calls to timeouts to the plain situation when the AI is just saying, oh, you know what, I don't want to do this job. Well, what you can do about this situation. So if you'll take a look at this, implementation partner, you'll see that to one side of the equation, you have extremely powerful abstraction, which is highly undeterministic, highly unreliable, and yet extremely powerful. On another side of the equation, you have engine, which was designed to actually mitigate things like that, to write deterministic and very durable workflows and implement them in a quite easy fashion. So if you take a look, it kind of makes total sense to combine them together. You use one engine to actually mitigate issues done by another. If you're seeking to implement LLM in your application, you're most likely going to start with two quite simplistic patterns, which in many cases probably going to be 80 or 90% of your whole LLM workloads. You're going to start with RAG pipelines. The pipelines that are designed to go to some data source, maybe vector database, maybe external website or anything, and gather information which is the most relevant to the user query, and return this information which, in a way that user or maybe other AI can comprehend and act on. From another side, you have type of the workloads which kind of doing the same. The only main difference is that now, instead of doing the return of the text to the user, you can actually perform some kind of arbitrary action based on a decision done by LLM on behalf of the user. It's as easy as that. You send email asking to cancel your order, well, and your order being canceled and account deleted. Well, be careful what you wish for when you work with LLM. See, looking deeper into RAG pipelines, and maybe in pretty much every paper which you're going to find about RAG pipelines, you will see they have like some distinctive steps. You always have parts that will be collecting and aggregating, normalizing, chunking data, embedding it into a vector store, maybe reshuffling or clustering it. From another side, you'll have parts which are responsible essentially for retrieving that and pushing the answer to the user. But what is the most curious part about RAG pipelines, if you'll take a look how they're being displayed inside these papers and inside pretty much every article people wrote, they all have distinctive steps. They all have these blocks and arrows between them, which surprisingly look exactly what we need. It is simply data workflow and data passing. I'll be showing examples today in PHP, but I think I'll do that mostly for visual purposes. It can be easily done on any language you love. In Python, Node.js, Temporal allows you to switch stacks quite easily. But if you're going to implement the RAG pipeline, the very simplistic approach is most likely going to look like that. It doesn't require much thinking. It's just a number of steps. Some of the steps will be used in LLM, like to summarize queries. Some of the steps are going to be going to external source to find this information and push it back into a pipeline. They can span for many, many actions, have some branching or some additional conditions. The action pipelines, once again, they're not that much different from temporal perspective. The only major difference is that instead of giving the response back to user, you're trying to act based on this response. And temporal makes this approach quite simplistic because when you're trying to act, you're trying to execute something within your environment, and temporal already connects to all of your environment. So gluing that to your activities and calling one of your services is extremely simple. If you'll take a look at LLM activities, and this will become important in a lot of slides, You will also notice quite interesting pattern. Every time you're trying to make an LLM call, first step what you're going to do is to assemble the context that will be sent to LLM, or prompt as we call it. This context, in a simplistic terms, can be represented as simplistic template. You just have a number of variables, number of things you found in a knowledge base, something you found from the user, maybe on the internet, who knows. You put them all together, and you just send them, and then you just send them to AI. You wait for this response from AI, and then you interpret the result in some structured form. The first thing we noticed while doing pipelines like that and writing actions like that it is actually extremely important to validate the AI response within a single activity. You can, generally speaking, get the AI response, send it back to temporal, and then do the execution in different activity. But the problem is you can't actually trust AI. So what will start happening is that in some cases, your activity will be executed successfully, everything is okay, your activity is done, but the payload that's been generated is actually completely invalid, and your workload just stuck. You cannot execute next activity at all. So it does make sense to combine them in order to make sure that you never leave activity with invalid data generated by AI. So far, if you will take a look at these workflows, they don't possess any threat to any of the engineers. They're quite linear. In some cases, it's dark. In some cases, you can even describe them in some DSL language. But at the end of the day, they are just temporal workflows. So the only thing you do is you replace some actions inside this pipeline from normal activities to the activities that go to LLM, and it just works. There is no additional magic, and there is no additional things you have to do except for just assembling this workflow. The problem will start arising once you start making this workflow long enough and complex enough to start processing more and more information. Because modern day LLM models, they're quite hungry for tokens. And some models can comprehend up to 1 million tokens, which is a lot of pages of the text. So if your workloads will be growing and information going to be passing, remember that temporal stores all the payloads that pass in and out your activities in temporal history. This will cause a very nasty problem later on, because you will never have a very confidence that your workload won't die simply because some LLM decided to write a poem instead of giving you the correct action. Oh. So the way how we decide to solve it and how you can solve it, you have multiple options. Option number one is to don't do anything, just write smaller pipelines. And in many cases, when you're doing something very simplistic, it just works. You don't necessarily care, and you can always retry or maybe just ask AI to be a bit shorter. In other cases, you can be a bit smarter and try to use implicit data referencing, where you're going to implement your own data converter and your own interceptor layer that will be detecting that payload is larger than you want, and offloading that to external data store to be used later. But what we found working the best for us, and that's the moment where I want to remember how prompts work, the moment we found work the best for us is to actually use explicit referencing. Because at the end of the day, all the information that you put to AI, all the information that AI is trying to act on, this information is actually only needed in a moment when you compile your prompt. You don't actually need any of this data or any of user PII inside your workflow. So don't do it all together. Just keep it outside and use the referencing using some links, some IDs, or database keys. This becomes handy when you're trying to assemble information from multiple systems, because by implementing universal referencing mechanism, you can actually combine information from multiple parts of your application and then just combine them all and resolve them all in a one distinctive place where you actually send information to AI. This way, your workflows will be completely free of any user information, and yet they will be used to orchestrate this process altogether. OK, so we have dark workflows, action workflows. We did the dereferencing. Probably nothing else we want to do. Users are happy, right? No. Users want not just to use a button where they click on something, expect something. They actually want to talk to AI, because that's how many of the users in the market perceive AI today. What you see in the picture is actually the GIF of one of the sessions we had with one of the agents, which, based on the user request, perform additional actions, run to some of the activities, and pull information in to give the correct answer. But implementation of these workflows might look similarly complex at start until you realize it's actually not that complex. Because the model of temporal allows you not only to write linear workflows that begin and end, but also the workflows in which you can implement such thing as a main loop. By making the main loop and running the LLM activity in it and populating this loop with information what the workflow receives using signals, you can implement quite sophisticated system that actually lives on a side with the user and answers his question in real time. At the same time, you do maintain whole state, and at the same time, you do maintain whole control of this process. You can see how much token LLM already consumed. You can see how fast it responds, and you can do the actions based on that. Implementation, once again, can be done in any language, but it can fit on a screen. It's not that large. Temporal makes it so easy because by exposing you to the code level, you can simply implement this loop like that, and voila, it just works. Also, by doing that, you're going to get a lot of benefits from composability model of Temporal, which means from the user perspective, while users send the message and go the response back, it doesn't necessarily mean you have to do a single action by going to AI. You can do something else. Specifically, before this message is sent to AI, what you can do is enrich it with additional context. Replace this block with your RAG pipeline that connects to your knowledge source, let's say information about your product, and voila, you have customer support bot that now talks to you about your product specifically. If you're trying to do long conversations or conversations that span for days and months, or maybe it's an email thread, sooner or later you're going to enter a situation that your context of your agent will be overfilled and the agent won't be able to act. Once again, because you run all of this process inside Temporal, inside main loop, it is exceptionally easy to detect this moment and see how much tokens AI consumed and use this approach to actually offload the past conversations and restart the new LLM session with conversational history. In essence, all you do, you summarize the past messages, you put them back into the history or context or the prompt, and you run again. The user won't even notice. However, from agent perspective, he starts from a blank slate, just knowing something from the past conversation. OK, so we can talk, we can see, what can we do? And that's the next thing which you're probably going to learn when we'll be working with LLM models. Most of them right now expose a new way for the models to communicate with your environment, and this is called tool calling. At the screen, you can see actually the agent creating the tool on demand, which later is going to be executed to run some analytical query based on user request. But what essentially you do to make the tool calling inside the Temporal, well, again, it's so easy. It's going to be probably the keyword in today's presentation. Because once you tell AI which type of functions it can call, and once you got these functions as a result from AI activity, all you have to do is simply map them to one of your activities or one of your workflows. Why not? Get the result and push them back to the queue. But be careful. What you want to do is to make sure that the message that user sends cannot be sent in between these tool calls. Otherwise, LLM model will die. They all want to get response immediately without any interception. Well, use the blocking mechanism and implement them inside your signal method. It's not that complex. Code, once again, is quite straightforward. All you have to do is to receive the list of tools you want to call, map them to parts of your system, such as activities, maybe other workflows, maybe something else, get the result back, and you can get this result in a sequential fashion. You can get this result in parallel fashion. Temporal provides you abstractions to do that in every language. Get the result back and push them back in a message queue. Easy. Next call that user does or AI invokes will receive responses, and AI will be able to act based on that. So if you have that, you have tool calling, and you have models you can talk. You have models you can communicate and that can look to information, that can execute arbitrary action, and in some cases do retries even by themselves. Like in many cases, AI will notice that tool call does not work. Let me try to do it once again. You might be asking, so what next? What can you do with these patterns? And the question you can ask yourself, do we even need a user? When you're running these workflows, they open you, while many challenges, such as hallucinated tool calls or skipping tool calls, they do open a huge amount of ability to run workflows or agents, in our case, agentic workflows, that will be executing by themselves autonomously, gathering information and writing the solution as they go. The main problem which you're going to have in this case is that while you communicate with agent directly, as a user, you can supervise him. You can say, yeah, you know what? You're doing it wrong. Please try something else. Don't call this tool. Give me information from different part of the system. When you run agents autonomously, you don't have the user. So what you should do, you should replace the user. And what can you replace the user inside the temporal workflows? Another workflow. So in this position, you are going to create your own supervision layer, which is essentially going to play the role of the user. And this supervision layer is going to be responsible for receiving the command, and you still need some kind of trigger, either webhook or user or something else. But based on this command, it will automatically form the first prompt or the first message and task the agent to execute it. The tricky part here is how to evaluate that the agent actually did some valuable work. First thing you might notice in applications like that, and this is a very nasty thing to see, that agents love to loop. Because the moment agent is making a mistake and trying to correct it in a very different way, but still incorrect one, he's going to make 2 error calls. And OK, I'm an agent. I did 2 error calls. It is in my context. Well, what should I do next? Probably make another call, because it seems so logical. So what you might see in some cases, that agent will try by calling your tools over and over and over again, especially when tools have been dynamically created, and fail eventually because of the self-destruct. They will simply overpopulate their context and will offload. Well, you just can't do anything. Thankfully, because you run temporal, you orchestrate and you collect all the information about all the tools that AI calls, all the payloads and all the errors. You can implement many mechanisms how to detect that AI is not doing what you want to do. You can do that heuristically by simply looking for the patterns in tool calls and seeing the loops when something happens over and over. Or you can do something more complex and use another AI model or another AI agent to actually look at the result and decide if this agent is faulty or the result has not been done to the purpose. You're going to be creating deeper and deeper deeper and deeper chains. Which kind of leads us to the next question. If you have one agent, why can we have many agents? Can we use them in collaboration, or can we use them by embedding them into much deeper chains of decisions and using them to run more and more sophisticated workflows inside your system? Well, the answer is obviously yes, because again, we're dealing at temporal conference, and there is nothing impossible inside the temporal. You will have to use mostly signals and workflows to compose applications like that, but the composition of applications that run multiple agents in parallel or have the collaboration factor is not that complex and not that different. In this video, we are seeing single agent that communicates and delegates a task to other sub-agents that will be executing tools written by other agents in order to execute some arbitrary command and return the result back to the hub, which user communicates to. To implement pattern like that, what we found works the best for us, and I'm pretty sure there's going to be a lot of patterns how you can compose applications like this. You are creating the common supervision layer, or how we call it agentic pool, a single place inside your workflow, which is the workflow, that essentially orchestrates the commands between multiple child workflows, or your agents. You delegate one of these workflows to begin to be essentially the hub or arbitrary agent, which you communicate from outside. That's your entry point, or maybe something which you communicate with user. And you let this agent to communicate with other agents. So how can you do that? Well, tool calling. From the perspective of your hub agent, the delegation of the task is not that much different from actually calling a single activity inside your system. All you have to do is to take the payload that AI decided to put to this delegated task and send it to other agent. And that's another nice place where temporal is going to help you tremendously. Temporal architecture, and especially the way how you write workflows, allows you to actually say that this tool call is not an activity. This tool call is a signal. And you can use this signal to send the command to parent supervisor loop pool that will automatically spawn the child workflow or your agent, delegate tasks to the child workflow agent, and will wait for the resultant signal that will be containing the resultant payload. Take this payload and send it back to your hub agent, and you have the ability to delegate tasks, while your hub agent doesn't even actually know how it works. It just thinks it did a tool call, which was very smart, and did some very good work inside. Another thing which you can do, and this is something which we experimented a lot, is the ability to start composing these agents and composing them in combination with more deterministic and more simplistic functions. You might create the process of code generation or code analysis, which spans for a very long time, Some parts of this process are very deterministic. Let's say do a Git pull. Some parts of this process are very simplistic. Let's do simple AI LLM analysis. We don't really need agents for that. But composing them together and using the ability of Temporal to converge few of these abstractions, but yet very powerful abstractions, to one common system inside the workflow, you can start creating deeper and deeper and deeper networks that are able to execute much more complex commands. But yet, while you're doing that, you still retain all the visibility. You still know every step that agent took. You still know every step that has been delegated or where the error happened, and you can correlate for that and you can compensate for that. Once again, if you're trying to implement that, at the end of the day, all you do, you create a number of processes that depend on other processes that depend on other processes. Doing that classically, possible. You can do it in many languages. Some languages specifically designed for that, like maybe Erlang, but Temporal makes it so easy to use on any stack, and Temporal makes it as well durable, because even if you shut down your worker, if you kill your agents, it will still complete, well, thanks to their model. So how do we use solutions like that? How do we use it for our own purposes? We create applications for ourselves and our customers that are able to solve arbitrary tasks that previously would require engineering time, which actually no one wants to spend. Do you really want to have a senior engineer creating your self-mapper for Excel every week because you have a new format received from a vendor? In this case, we found that there is a huge amount of patterns and a huge amount of parts of the applications which we don't actually want to do. So let's ask agents to do them. We can ask agents to create them, to validate them, execute them, and test them as they go, spending not weeks, but minutes to get the working result. So why do we think Temporal is the best solution for AI? Well, if presentation didn't say about it explicitly, they made in a completely opposite spectrums. This very powerful abstraction that allows you to run NLP and, generally speaking, thinking to execute some action is kind of pointless to run on itself. You need to embed it to something. And Temporal provides a very rich environment to make this embedding so easy and so simple and at the same time so durable. So combining them together allows you to create very complex chains and very complex applications that can be pulling information from many sources for the span of minutes, hours, maybe days, and then execute on them to provide you result. I can talk about that for days, maybe weeks, but if you guys want to chat more, please visit us at our booth, or let's get a drink later today. Thank you. I guess any questions? A lot. But how much engineering time cost?
No, I'm just curious.
Significant amount for like a medium-sized company, but the way that we can iterate on a pace that we never seen before, like in many cases, we can receive the working POC in 20 minutes on a call with stakeholders. Like this process will involve 5 people back in the day. We don't want to use AI, and we don't want to use it for everything, because we kind of don't trust it in many cases, but it's always going to be the use cases in your work and your process which you just don't care. Mappings, API calls, data transformation, something you can easily verify and see by your own eyes. I think there's something.
How do you evaluate the agentic AI?
Well, you evaluate it. Sorry?
Can you repeat the question for the recording?
How you evaluate agentic pipeline. Well, that's a beautiful part about Temporal. From the Temporal perspective, agentic pipeline is a huge workflow, which, yes, you can test by the steps, and you can make sure that all of them work from the workflow perspective. However, from the user, when you send the command, it's just a function. So you evaluate result by evaluating the quality of the function result. If you're doing something that is going to be fetching information from your database, like RAG pipeline, there is a bunch of solutions on the market which can run it and see how well it correlates with actual information. So you evaluate result without actually evaluating all the steps taken inside. You kind of don't even worry about them. Agent is willing to do what he thinks is the best. Yeah?
Why were you choosing child agent rows instead of just saying two calls?
Sorry? Why would we choose using the child agent if so? Good question. I mean, the reason for that is because the context window of each of the agents is limited. It's quite large, but still it's limited. So if you have to perform a simple action that can only be done based on information that can be collected from many different parts of the system, by just collecting this information, you're already going to overpollute the memory of the agent, and he's going to just be working much slower and much harder and much more expensive. So instead of that, you want to isolate this process and only get the result.
How do you run the AI generated tool? Because it can be in different language, right?
How do we run what, sorry?
AI generated tool.
We run it right in the temporal. So like the thing I didn't say in that presentation, the referencing layer, which was a single slide, is actually where we spend the most of our time. Because when agent defines the tool, we actually define it as part of our system, which we use temporal as syncing layer to sync it to our runtimes, which makes it immediately available for AI to use. So basically, by AI creating the tool inside the system, it automatically declares it and makes it available to AI if it's been connected, in declaration of this agent. It can be any language at the end of the day, and we think that eventually the language, when you work with the application, is probably going to matter less.
Is there any other like temporal specific limitations or things that you ran into that you didn't expect?
There's few, but I mean, they're not that large and they're not that much different from what you will do in temporal. If you run a very long decision chain, the agent that can span for many files and run many iterations, you're eventually going to run to the position then when your workflow just has to be restarted. And restarting the workflow that has hundreds potentially of child workflows in a tree is quite a challenge. So you might need to implement your own mechanism to properly collapse all these workflows and restart them over in the next iteration. Well, right now we validate it by the user observation. You just test it right in the mix, so you see if it works or not. We don't try to create, huge application servers using these tool calls. We just create simple integrations, which are much easier to test. But at the end of the day, you can actually feed this tool back into the agent, and that's another property of the reference layer we create. Every tool that agent create, they actually become part of the knowledge base that agent can use to learn to create new tools or read existing tools and analyze if they work correctly. Or they can just generate the test.
We have one more question.
Okay, I wonder if you have any advice in terms of how to deal with the throughput of the LLM models themselves. Typically in an environment like this, you would have a shared LLM resource, and it can get pretty overloaded if you have, let's say, a big chat.
Well, you can move the LLM calls to the separate task queue and have a rate limit on this task queue. That's about it. But in our case, we actually have our own backend that encapsulates all the LLM calls where we have additional priority queue with additional rate limiting. It's a simple kind of side effect that we allow multiple organizations use the same model, but at the same time, we can split the model use between organizations, so they never collapse in this regard. But at the end of the day, even if you don't have it and it fails, well, it's just going to be retried.